Well, I'm not sure if any of you'll remember, but back in those heady days of 2017 when, well, the world was a free and different place, I actually went ahead and we built this mini CNC machine. Now, for whatever reason, I never really got a lot of use out of this little CNC machine, and I think that's mainly because the machine itself was quite easy to build, but the actual learning curve of using the software and actually generating the toolpaths, the G-code to do that, back in 2017, that was quite difficult to do. So unfortunately what actually happened is the little milling machine got put in a box and forgotten about for 3 years because I didn't really have a good reason to use it. Well, one of my friends, Paul of the Cody's radio channel, he asked me if I could actually help him out with a little project that he was doing, and he wondered if we could use my little CNC machine to do some engraving. Well, I've got to admit, I've got no idea whether we can do it or not, but I'm prepared to give it a bash. Now, in the 3 years since I built my mini milling machine, there's actually been quite a few upgrades proposed, and one of the biggest and most worthwhile upgrades is actually to upgrade the spindle motor to something more powerful. So as it comes with, the motor that's actually on here it's meant to be rated about 10,000 RPM, but I believe quite a worthwhile upgrade is actually to put a bigger motor in, so that will run up to 20,000 RPM, and because we use such small cutters, it is a good idea to run them fast, because they only take very little bites out of the material. So if you run them a bit faster, you get to take more bites and you get to remove more material. So what we're going to be looking at today is upgrading that motor. We're going to change the tool holding by installing a Collet Chuck, and because we've put a bigger motor on it, we need more power. So we're actually also going to replace the power supply that comes with this with something a bit more beefy. So let's crack on. Well, I'm hoping that you're going to be able to see that I've gone ahead and I've just set up a dial gauge onto the shank of the tool in our little mini milling machine, because I was hoping to show you what the run out is on there. So let's see if we can do that. I'm afraid my big hands might be in the way, I can't really avoid it. So at the moment I've got this zeroed out, so I've actually turned the spindle. So that goes to around about, I think that's just over 5, around about 5, so that's 5,000th of an inch. I keep rotating it. It does go back to the 0, and that's fairly repeatable. So basically what that means is our little milling cutter here, it's running eccentrically, and this only gets exaggerated by the length of the tool bit here, so probably it's running out even further when we get to the very tip of the tooling. Now, for a machine as basic as this, I don't really think that amount of run out is totally excessive, but really it's just to do with the way that this little tool holder is manufactured. It's just got a grub screw on each side of it, and I'm sure that if we actually tweak these grub screws, we could probably improve it, we could probably balance that up a bit, so that's a little bit of effort. Now, we've also got another couple of grub screws here right at the top of the tool holder. There's actually one on each side of it, and again, if there's any eccentricness, if there's anything off centre, maybe even just the amount that these two grub screws have been wound in and they're in contact with the motor shaft, that's going to throw everything out. So again, I think we could improve on that by fitting a better tool holder. I mean, basically I haven't discovered this, I'm just reporting what other people have said, that these little cheap tool holders are pretty bad. So we're going to replace that with something called a Collet Chuck, which should be able to grab our tool down here much more accurately. Now I'm hoping that that wobble in the spindle, I'm hoping that's all in the tool holder. I think we can probably check that by going off the spindle itself. So let me just set everything up again. So I've now moved the tip of our indicator, so it's actually rubbing on the spindle itself. So if I now rotate the spindle, hopefully this should stay nearer to 0. Okay, well as I touch it you can see that it moves, but as soon as I take my fingers off, it just go back to 0 even when I do a full 360. So the run out here, it's in the tool holder, it's not the actual motor spindle, it's all in this brass coupling here, that's where the problem lies. So we're going to replace that. Now hopefully one of you out there has got a pen and paper, because can you write that down? So the run out is 5,000 at the tool here, so we need to remember that. One of you write it down and tell me later. So this is the motor that originally comes with the machine, and as I said earlier, this one is rated for about 10,000 RPM, or certainly that's what they say. I intend to replace this with a motor that's a lot more powerful, can go a lot faster. In theory, the one we're going to put in there can do 20,000 RPM, but I think we just need to actually benchmark that and actually find out how fast this is going. Well, as you saw earlier, I've got a little V-shaped milling cutter installed in here. It's actually an engraving cutter, and these are terrifyingly sharp, so before I end up cutting my finger off, I'm actually going to take this tool out, because I will end up cutting myself if I'm not careful. So there you go, that's a little V bit. So the next thing I want to do is measure the spindle speed. So I've just gone ahead and bought this digital meter. So this isn't an unboxing, although I haven't seen what's in here, so we are opening this for the first time. Again, the main reason that I bought this is because it was on Amazon and it was cheap. So here we go, it's a little tachometer, uses some form of a laser which it bounces off. And we need to put some little reflective strips here onto our spindle, because this will have a little laser on of some description, and it will bounce the laser back to this sensor here, and it should count the pulses and work out what the speed is. Now the reason that I chose this particular tachometer is because it actually happens to be the cheapest one on Amazon, so whether it's any good or not I don't know. Okay, so we get a splodge of red light for maybe entertaining the cat with. So okay, we need to put a little sticker on here. Yeah, that didn't work. Okay, I think it might be because my fingers might be a bit greasy, so we're going to go ahead and just clean all this off, and we'll have another go at that. I'll bring you back shortly. Well, as you can see, our little motor here is meant to be rated for 10,000 RPM, but it's actually only doing about 8,500 at the moment, so it's actually running a little bit slower, and I suspect it would run slower still if we had to put some load on that spindle. So I'm powering our motor from the benchtop power supply, and it's drawing about half an amp at the moment. It's drawing 456 milliamps in fact. So obviously it does draw a lot more current as we load the motor up, and we'd expect that. Now unfortunately my power supply here, that only goes up to 3 amp at 24 volts. I've got another power supply next to it, but that one only goes to 20 volts, but let's give that a go as well. So it looks as though when we load our motor up we can draw up to 5 amps from it, but I think in the real world we'd never draw anything like that. So I think we'll take this old motor out because, yeah, we're going to put a more powerful unit in. Now unfortunately we can't actually power this motor from this milling machine control circuit, because the output MOSFET, which pulse modulates the motor current and controls the speed, I don't think it would be up to powering this motor. It certainly would stand a chance of burning it out, or a few people have tried just upgrading the motor and they've ended up burning up the MOSFET on the board. I don't want to do that, so when we actually replace this motor we're going to actually build a new MOSFET driver for it as well, I think. So just looking at the motor, it says here that it's an XD775, it says the voltage is 24 volts, revs per minute is 20,000, whereas this motor, the old motor, this had a rated speed of 10,000 but it was actually only doing 8, so it'll be interesting to see if this one's actually any faster. Well, I'll tell you what, before we pop it in there I'm going to install the new Collet Chuck on it. So here's the new Collet Chuck that we've bought. Now in theory this should be much greater precision, and it should actually be easier to put the bits in and out of. So here's our Collet Chuck, and it is covered in, it's covered in horrible preservative grease. Let's wipe some of that off. Now for reasons that I don't actually fully understand, I do happen to have 2 of these motors, and they both say 775 on them, and they do look identical. I can only imagine that I accidentally purchased them twice from Amazon. I don't know what I did, who knows. But looking at this one, this has got a longer shaft on it, and the shaft on this one is shorter, and it's got a half grind on it so that the grub screw would engage on it. But I actually think that the fact that it's actually got half the shaft ground away, that would mean that it could be more liable to start wobbling around. I'm actually wondering if a better choice would be to install this one. Well, unfortunately, this motor that's got the full shaft on it, I don't think I can get it on. The machining feels a little bit tight. Now, they are made to very high tolerance, these things. So I think I might have to go with this one after all. Well, that was actually doing over 20,000 RPM there. It was actually going faster than the manufacturer said it would, so that's quite impressive. And I did also notice that my power supply was actually going into current limit, so I actually think it maybe would go faster than that again. Okay, that did make a difference, because running from 20 volts it was only achieving 16,000. So I think that this will do well over 20,000 RPM. I'm just a bit worried about the balance of it. That did sound as though, well, it was quite loud, so it kind of indicates maybe there's something slightly out of balance somewhere, and I'm not sure where that somewhere is at the moment. Could be that I haven't got the collet quite cinched down or set as well as it should be. Now, of course, this is going to sound totally different anyway because it's not being held in the same way, but we'll give it a go. Ooh. Well, that sounds quieter, doesn't it? I think we need to just pop this collet off again. It's maybe this collet that's creating all the humdrum. So it does appear that a lot of the noise does seem to be generated by this collet, so it could be that I've got something out of balance. So I think that's going to need a little bit more investigation, isn't it? Okay, so I've been messing around with this for about 5 minutes, and it was actually quite easy to figure out what the problem is here. It is running out of balance, and the reason that I think that it's out of balance is because we've got 2 grub screws which actually hold this collet onto the motor shaft. And the motor shaft itself, it's ground on one side, it's a stepped shaft, so that it's got a flat on it. Now the idea is that you would tighten up the grub screws, and one of the grub screws will tighten against the plain section of shaft, and the other one will engage on the flat section of shaft and stop it from slipping round, stop it from spinning. But the problem is with these collets is when I actually try to wind out the grub screws, they actually don't come through into this centre hole. The very tips of them emerge, but certainly they don't come deep enough to make contact with this flat surface. So we're only getting any retention with the collet on just one side. So I think what's happening is it's actually pushing the collet to one side when we tighten the grub screw up, and it's throwing it out of balance. So there's a couple of potential fixes that we could do here to get around the problem. One of those fixes is probably to take this collet and actually just get a tap and run it through so that these grub screws can actually move fully in and out. Although if I actually did that, I suspect that there wouldn't be a lot of thread left on here. You'd probably need a longer, deeper grub screw, which again could throw everything out of balance again because of the weight on one side compared with the other. So I think what I'm going to do is, luckily I said I'd accidentally ordered a different motor, so this motor is different. It's got a plain shaft on it. It doesn't have a flat grind on one side, although amazingly enough the shaft is considerably longer. So I think what I'll do is I'll take this into the garage, and I'm going to cut some of the shaft off this motor to make it the same length as the original one. I'm going to cut that down, and this will be made out of some hard material, so I say I'm going to cut it. What I'm going to have to do is I'm going to have to put it in the angle grinder and slice it off with an angle grinder, and then just put a little bit of a chamfer on the end with a honing stone. So I'm going to go ahead and do that and bring you back, and I'm hopefully that should help. It should make a bit of difference, but I don't know, who can tell. Okay, so I've just gone ahead and I've cut the shaft down on our motor here, and I'm hoping that this is going to be a better fit onto our collet. I'm hoping the fact that it's actually not got a step shaft on here, I'm hoping that this will actually centre itself better. What you could do, of course, you could come back here with a little tiny drill. You could take the grub screws out and you could dimple the motor shaft with a small drill and do it that way. That would, that would be instead of having a flat on here. So what I'm going to try and do is I'm not going to count the turns. I'm going to try to almost do it using a non-existent torque wrench. So I'm going to try to nip these up equally. You know, looking at this, I'm still seeing a little bit of wobble. I think that maybe, believe it or not, these Chinese collets may not be the highest precision. Now both of these motors have exactly the same part number, and there's nothing actually wrong with the motors themselves. It's just that this one has this step shaft which throws the collet out of alignment. I'm sure that if you're prepared to put some effort into it, you could sort that out. You could maybe put some packing material on here, or maybe just turn the shaft round so that the grub screw wasn't trying to engage on it, or maybe it would have been fine just to have put a deeper grub screw in. But certainly what I'm saying is, when you buy these things, there's obviously quite a lot of variation. I mean, even the shim that went round the motor was a different thickness. This one, I can see, it's this one that we actually put on it's nearly twice as thick as the other one. So yeah, what can you say? I guess you get what you pay for. These motors aren't particularly expensive in the scheme of things. They're about, I don't know, I think they're about £15. It's different if you'd have paid £400 for a spindle motor, of course. But yeah, I mean, it makes you wonder how many motors you have to buy before you'd actually find a good one. So the original one was 5 thou, and our new high precision one is 20,000 thou. So I don't know. We will try nipping up this collet, but I don't think it'll make any difference. I just think it's probably poorly machined. So buyer beware, I suppose. Buyer beware. Well, after our little collet disaster there, I'm going to have to drink this large glass of gin to calm my nerves, I think. Now, I guess we should actually see how much current this new motor draws, because I don't think there's anything wrong with the motor. It is just a problem with the collet. So at the moment it's on the 24 volt power supply. I suspect it might draw too much current and go into current limit. So that's drawing about 1.5 amps, isn't it? So it's drawing about 3 times as much current as the old one did. Well, not exactly hot off the press, but I guess it is kind of hot. Here's the cover that I've printed for our power supply, so yeah, let's hope that it fits. So I've actually designed this just to slip over the front of it here, so that it kind of gives us a little bit of protection from some of the exposed metal parts on it. So will that slip onto there? Okay, so that does fit. Maybe a little bit loose, but it's always difficult to get the exact tolerance, isn't it? Now, for some reason my holes appear to have gone a little bit oval rather than being round, so I don't quite know what went on there. And I've also just noted that the mounting holes on here aren't symmetrical. We've got 2 mounting holes here for screwing it down, but there's actually only one of the holes exposed here. This other one, yeah, this other one isn't. It's being used to hold the case on, so yeah, that's not very good, the fact it's not symmetrical. I should have noticed that earlier, but I think this should be okay. So it's got the infill pieces on here from left over from the 3D printer, so we need to try to carefully break them out. Was that carefully? Maybe not that carefully, was it? So this is going to be the fuse holder for the mains fuse. At one point I thought I might actually fuse the output from the power supply on here, the 15 amp 24 volt output, but I don't think I will. I think I might put the actual fuse for the power supply on the main part of the CNC, so that's a bit loose, but that will be fine. What else have I got to go on there? I've got to put an IEC connector on there. I think we've got one. Now I've got to remember not to snap this fully in here, because I've got to wire this up. If I install it now I won't be able to get it out again, so that'll be a problem. And then on this end we should be fitting a rocker switch. So here's my rocker switch to turn the unit on and off. And again, I don't want to clip that in all the way at the moment because I'm going to put some wires on it. So that's going to go on there. And finally I've got a connector that needs to go onto there. So this is going to be the power connector that I'm going to use between my CNC machine and this power supply. So we've got some chassis mount connectors, and that should be installed in this hole here. And again, that fits as well. Now some of you might be wondering why I've gone for a 4-pole connect, because we're only supplying 24 volt DC to the machine, so why have I gone for a 4-pole connector? Well, the reason is because I'm going to use the first 2 poles for the 24 volts, and then the third pole I will probably use to actually carry an earth through to the body of the CNC, just in case something goes wrong with the actual 24 volt switch mode power supply, because it isn't impossible for these to actually leak some AC through them. Quite often it's not actually a fault, it's just to do with an RFI capacitor that they seem to have installed across primary and secondary windings of the switch mode transformer. I don't know even if this would have that problem or not, but it just seems like a good idea. If you've got a metal piece of machinery, you're going to plug that metal piece of machinery into a sensitive USB connector. I think it's probably a good idea to earth that piece of machinery. So that's what I'm going to do. So first 2 pins are going to be plus 24 volts, 0 volts, and then maybe an earth connection. Now I have also noticed with this power supply you've got to be a little bit careful regarding the length of some of the screws. Looks like the ones on the side here are okay that we're going to pick up, but certainly some of the ones here which are underneath the power supply unit, if you were to use a screw that was too long, it would actually touch the PCB. It would go through the metal cover and it would short out on the inside of the PCB. So I guess if you're looking to screw one of these power supplies down to something, if you buy one, just be careful with the length of your screws, because you could drive them into the PCB if you weren't careful. You would assume that these 2 holes here would be symmetrical. They would be on the centre line of the power supply. They're not. One of them is about 14mm from the bottom and the other's about 12 from the top. And of course it's got 2 holes on this side, but as I may have said earlier, there's only 1 hole on here because the other hole is being used to actually hold the cover down. So yeah, it could have been built kind of symmetrically, and for whatever reason they didn't do that. But I guess the main thing is, will this power supply work? Well, I've got to admit, I've got no idea until we actually wire it up and plug it in. So, well, yeah, I guess that's the next job. So I haven't got a huge amount of room to reach in here and actually make attachments. So I think what we'll do is we'll assemble as much of the wiring outside this case as we can, and then finally just pop all the connectors in afterwards. So it does appear here that the fuse holder that I'm going to use has some kind of non-standard maybe crimp sizes, so I'm not going to use crimps. We're going to have to solder something onto there, I think. So today I'm using this cheap pair of Amtec crimp pliers, and they are very cheap. I've got to admit they're not very impressive. They actually seem to be quite intermittent for how tight they put the crimp on. Quite a few times I've put crimps on with these things and it's just fallen off. So what I've done is I actually cranked up the positive setting so that they actually crimp down harder. But yeah, they're very hard now. There seems to be not good adjustment on them. They either crimp far too hard or they don't crimp hard enough. So these two, so this red and the black wire, I think we'll use these for the 24 volt output. And one end of these will have to be soldered onto our connector inside here. So I think I'll use this blue and this brown wire. These are going to come from the switch and these are going to go to the 230 volt input on the power supply. That should be more than long enough, I think. So this is the neutral wire from our IEC connector, so this is also going to go directly to one side of the switch. I'm not sure which way up I'm going to put the switch yet. I seem to think that people put switches different ways up in different countries. Don't the Americans do it oddly, or rather maybe they do it correctly. I was always told that you should put a switch so that the off position is kind of, I'm going to say the lower part sticking out. The idea being if you fall on a switch, or you want to switch something off in emergency, it's easier to push a switch down than it is up. I seem to think though that they actually put the switch different ways up in different countries. Yeah, leave it in the comments. So we're going to take our mains input here through our IEC connector, and I'm going to take the live side directly into the fuse before it goes to the switch. Now I've had a look through my box of crimps, and this fuse holder seems to be what I would just call a non-preferred size of crimp. Certainly it's not preferred by me because I haven't got any. So what we're going to have to do is we're going to have to solder the wires directly onto the back of the fuse holder. Now it's always quite important when you're actually soldering these fuse holders. You can see that this has got a connection at the back and the one at the front. So you always want the incoming side to the far end of a fuse holder, because if you actually have it to the front like this, there's a chance that if you was to pull the fuse out, you could actually make contact with this live side as you pull it out, whereas if you actually connect to the far end of the fuse holder with the incoming mains, it's actually disconnected when you take the fuse out. It actually pulls away. So if you're wiring up a fuse holder, the live wire always goes to the end, to the back end. It never goes towards the front. Well, I've got to admit, when it comes to these fuse holders, I have always been slightly puzzled why they do tend to have these two output terminals on, because, well, you generally don't need two outputs from a fuse, you only need one. And to be honest, having two is just somewhat annoying in that they do get in the way and you end up having to put some insulation on it or something of that nature, because these two lugs here, they are soldered to the same point within the fuse holder, which is the end connector. But yeah, why do you need two of them? Most fuse holders do seem to have two for some reason. I've got no idea why. Now these fuse holders are actually donkey's years old, so they're very dirty, so I'm just giving them a bit of a clean. Now no doubt this will now fight me every bit of the way trying to get the locking ring on. Right, that's it. And we're going to use the old super adjustable spanner to tighten that up, I think. So I'm going to need you guys to remember what wire goes to what on here, because I'm bound to forget. So get your thinking caps on. So I think we'll have number 1 as live, number 2 as 0 volts, and number 3, I think we'll have that as our earth. So we can just do the final assembly on this now. So we've got terminals 1, 2 and 3, they're plus 24 volts. Then we've got 4, 5 and 6, they're 0 volts. Then we've got 7, which is earth, 8, which is neutral, and 9, which is live. Does it recommend a fuse size? No. So I'm guessing the correct fuse to put in here is probably the one we can find. Ideally it would be something of an anti-surge nature, so probably 3 amps would be in the ballpark. That's a slow blow fuse, I can tell because it's got a coil of wire inside it. It will have quite a high inrush, this power supply, because it's a switch mode. If we get anything a bit smaller. Okay, here's a 2 amp time delayed, so I think that's probably close enough. something just dropped out of that power supply then. Hopefully it was nothing too important. Right, I think we just need to give this a try, don't we, before we go any further. So let's see if we're going to work or it's going to go bang. Okay, well, the switch lit up. Okay, I'm guessing that that did something. I did say I wasn't sure which way if I was going to put the switch. I still haven't made my mind up which way up should we put it. I suppose it depends which way up the power supply goes. I think based on what I said earlier, falling on it should turn it off. That is the off, so I'm going to put it that way up. So, on, off, on, off. Now I've noticed this, it's got a fan on it, but the fan isn't running, so it must maybe have some temperature control on it, I'm guessing, so that it actually, the fan only comes on when it's actually, you know, dissipating some current and it needs cooling, so it must be thermostatically controlled, or plan B is the fan doesn't work. I don't know. So we can now go ahead and screw this cover down and probably short out the internals. Right, I'm going to have to delve into the screw box of despair. Probably won't be able to find any in here either. Okay, we have one screw. Oh, wait a minute. There's another one. So it does look as though if you put too long a screw in this side, it will actually drive into the side of something which is possibly vitally important. So let's just do a bit of rearranging there. Okay, well I think that doesn't look totally rubbish, does it? I'll have that. Let's just do a quick safety check to make sure the body of our power supply is in fact earthed, because I'm hoping it will be, which it is. And we should also have an earth pin on here, of course, which we do. Okay, so we've got 24 volts. So it's kind of working, isn't it? I'll take that as a win. Spoilers. Okay, so I've come out into the garage to take a closer look at our vibration problem between our motor and our Collet Chuck here. And as you can see, I've just loosely clamped everything down to the bed of my milling machine here, because the bed of the milling machine is pretty true, it's ground flat. And we don't want all the wibbly wobbliness of the actual CNC milling machine affecting our reading. So this is all much more rigid and it's better for taking measurements. So I think I'm seeing about 2 thou there, which is still more than I think I would like to see. So I think I'll just reposition this indicator towards the end of our Collet Chuck body now, and I suspect the problem may be exaggerated. Okay, that's zeroing. Well, as you can see on the gauge now, we now seem to be out from about 10,000. So the problem's gone from 2,000 to 10,000. And now I've actually got a reference on the end here to look at. I can actually see that this this Collet Chuck, it's running eccentric. It's as though the internal bore isn't parallel with the external bore. Now it could be being kicked over by these grub screws, that could be the problem. Now the problem's only going to exaggerate the further we move away from the motor here, so yeah, let's well, actually I'm going to take this tool out, and I think what we'll do is we'll find a 3mm twist drill. I'll get a brand new precision twist drill and we'll stick that in there and we'll indicate off that. So I'm just going to reposition our indicator on our drill shaft here, and I suspect that the problem is going to be, yet again, it's actually going to be another order of magnitudes worse still. So let's just centre that on our 0. Yeah, and our problem is getting even worse. And now I can actually see it. I can actually see how out of line this actually is. Yeah. Let's see if I can bring you in. Hopefully we can show it up on camera. So I'm hoping you can see the difference between our drill and our pointer there, that the drill is clearly wobbling up and down, so the whole chuck is running eccentrically. Yeah, so we've got a definite wobble there, haven't we? Well, I guess it would actually be very lax of me if we didn't actually just check that the motor shaft itself wasn't bent, because that could be the cause of our problems as well. Well, that's the motor shaft itself that I'm just spinning now, and I've got the gauge set up on it, and as you can see the gauge isn't moving at all. Now the problem would be less going towards the motor, it gets accentuated as you come out from it, but I'm not seeing the needle move at all there, so I think we're actually good to go on that. So I think the motor's okay. So I think the problem is in our chuck. Well, as you can see, I've done various tests trying to get to the bottom of this source of the eccentric running, and I think it's very simple, that it's just machined badly. The inner and the outer bores aren't parallel with one another. So just for the final check again, I've actually got this set up on where the motor shaft would normally go. I've got the grub screws taken out, and I'm actually running it on the back of a twist drill, but the twist drill that I'm running is you know, it's a brand new drill, and I'm guessing that the shank of that drill is going to be very straight, but in any case it isn't spinning, it's not rotating, so it shouldn't make a difference. And then I'm going off the business end, which is the internal tapered bore of the chuck here. So in theory, if I twist this, we shouldn't get any movement at all, it should be fixed. And as you can see, it isn't fixed, and even I can see it just by eye. This is actually wobbling up and down, so the hole that is drilled through here, it's not in line, it's not in line with the outer bore or the grind on the end. So it really doesn't matter what I do. I mean, yes, you could try playing with these grub screws and tightening them up, but I think the reality is you're on a hiding to nothing, because the bore isn't drilled correctly in the first place. So I'm guessing the only thing that you might be able to do is, of course, you could maybe set this up in a 4-jaw chuck, and you could re-drill it, but that's no good for me, because if I did drill it bigger, it would no longer fit the motor. So I'm guessing that what you'd have to do is, I don't know, put a plug inside it, maybe machine it out, oversize, press fit a bush into the inside of it, and then put the whole thing in the lathe and then remachine it to 5mm. But I think, to be quite honest, that's just more trouble than it's worth, and I think I'd rather just try to buy another of these chucks. So when it comes to buying these chucks, the quality is dubious, and it's a shame actually, because the actual chuck part, the collet itself, looks to be really quite high quality and nicely done. It's this, I'm going to call it the arbor. It's just this arbor that's very, very poorly machined. Yeah, I can't do any more with that today, so I guess when you're buying with these chucks, you get what you pay for. If you pay £9 for a Collet Chuck, don't expect it to be very good. This is totally useless. The run out is so high, the machine will just shake itself apart. So we're going to have to think again.